Good day, everyone. Thank you very much for joining me. Now, today's presentation is entitled Minimising the Environmental Effects of Consumerism, and I've put a little subtitle here, which is a very limited introduction to the concept of life cycle assessment. I want to stress the terms very limited and concept. All I can hope to do today is give you a basic introduction to some methods that you might be able to deploy if you're thinking of getting a product that perhaps you don't already have or replacing a product that you do already have. Let's get on with it. First of all, what are we going to talk about? We're going to look at a very basic introduction to the concept of manufacturing and through life emissions. So my premise through this talk is going to be that we are going to make a choice as to which product to buy or use based on its total through life emissions, nothing else. Now, at the end, I will address the massive elephant in the room, which is money. But for now, we're going to assume that money is no object and the products have equivalent usage. That's problematic in itself, but we've got to start somewhere when we start looking at these concepts, and that's the assumptions we're going to be making mostly in this presentation. We're going to look, based on this concept of through life emissions, at the comparison between two available new products. For example, you're going to the shop today with a bunch of cash and you have a choice of two items. Which one do you buy based on your knowledge of the total emissions that that product is going to generate? We're going to look at a more common scenario, I guess, which would be whether or not to replace a product that you already have. So how to compare a new product to an existing product. Now, what I'm not going to do here is go into how to compare a second-hand product to an existing product that you already have, because that's effectively a grey area between these two, and that's a very individual assessment that I can't answer in a more general way at this point. Finally, we're going to look at some worked examples, and I'm going to use a fairly bog standard worked example, which is cars, so electric vehicles versus internal combustion engine vehicles, because those choices are some of the most dramatic that can be made using this model. Now, of course, again, I will cover this briefly, but the best thing to do is to get rid of your car and not have a car. But assuming that that's not an option or we don't want to do it, we're going to look at how we could compare a couple of products. At the end, we will have a very brief discussion of some of the economics and politics involved in this model. Now, that's not to say that I'm going to be able to solve these problems, but I am going to give you maybe some tools that you can go away and use when it comes to lobbying your own politicians in your own local areas about things that they might be able to do in order to skew people's behavior towards a more environmentally responsible direction, if indeed you believe that that is necessary and appropriate use of government's time. I am aware that there are very large swathes of political thought that think that that is not the role of government, but although this presentation is not discussing global climate change, I have discussed global climate change at some length in my offshore wind series, and I think that I don't really need to justify anymore that global climate change is a very, very serious problem. So at this point, we really need to do what we can to solve it. And if that means altering people's behavior, then I'm afraid people's behavior needs to be altered, because otherwise the vast majority of people on Earth, maybe not you and maybe not me, but the vast majority of us are going to have a substantially worse time than we already are. Okay, with that in mind, let's kick off. When we look, first of all, at the most basic case, which is a comparison of two new products, we have time here on the horizontal axis and we have the cumulative emissions on the vertical axis. Now, pretty much any product is going to have a very, very sharp immediate spike up during where it is made. Now, in practice, this line is generally going to be almost vertical, but I've sewn it slightly off vertical because I want it to be able to be seen and visible. So here we've got the emissions from manufacturing. And what will happen then is the item will be delivered to its warehouse or shop, and then it will be sold, and then it will be used. And depending on what the product is, it will have some sort of emissions during its usage period. So a good example of that is anything with a power cord. Anything that you have to put power in, like a computer or a kettle or a car or something, is going to use energy. And generally speaking, energy is equal to emissions. And there's a general rule of thumb linking those two together. Now, that is not always the case in every country, and we'll go into that in a little bit. But for this very, very simplified model, we can assume that a product is going to be used and it's going to generate emissions. Now, you know as well as I do that if that product is going to be repaired at some point, then it's going to need new parts. So that will generate more emissions because those parts need to be manufactured, and then we might use the product again, and then it might degrade a bit, which means that it will actually run less efficiently, so its through life emissions will increase, and then we need more repairs and so on. That is all well and good and true. Those kind of caveats totally exist, but for now we just want to assume that we've got this very simple model of constant emissions during manufacture, and then a different set of constant emissions during use. Now, for an individual case-by-case basis, we can examine this line more detailedly. Now, the other thing that I'd like to mention here is that the emissions is a catch-all term, which for this purpose I'm pretty much always going to assume is a concept called CO2e. Now, CO2e stands for CO2 equivalent. Now, you don't need to tell me, I know this isn't perfect. Obviously, when we create something, we have emissions from the energy that's used to create it. We have pollution caused by mining the raw materials, by transporting it, by wastewater, and so on and so forth. Many different types of emissions. What CO2 is an attempt to sort of lump all of those emissions together with some sort of metric that relates to how bad it is in terms of global warming relative to CO2. So in general, we're going to assume that anything that we emit is going to create global warming, and it will create global warming in some proportion to raw CO2. And when we add all those figures up, we'll get the total equivalent CO2 that that product has produced. Now, usually, because many things are worse than CO2 for global warming, that CO2e equivalent figure is going to be higher than the CO2 produced. Obviously, there's severe limitations to this, and it does not take account, in this particular case, of various other forms of pollution, which may be just as bad in some instances. So we have to start somewhere. This is where we're starting. If we then add a separate product onto the same chart to compare it, in this case, we're going to use this green product here. This green product also has a manufacturing emissions and it has a usage emissions. But in this case, for whatever reason, the green product takes more energy to manufacture, but in use it uses less energy. So what that means is that after a certain period in use, the total lifetime emissions of the green product are going to equal the total lifetime emissions of the red product. And if the green product lasts longer or remains in use longer, then the total lifetime emissions of the green product will be lower by this amount here than the red product at any point in time. So let's call that time at point 0. Now, this is a fairly simplified model, but it is a useful model, and it's a model that we can use with various degrees of refinement in the real world. Let's continue to look at some examples based on this very simplified model. A good example would be the comparison of almost any good quality electric vehicle, which might have a curve like this, to any good quality internal combustion vehicle, which might have a curve like this. And at some point, there's going to be a break even, and beyond that break even point, the EV will almost always win. Now, in this case, I've used two examples from Nissan because it's a manufacturer that makes both. I can hear you screaming about the electric vehicle needing electricity and so on. As I keep saying, and did during the wind turbine video as well, that is irrelevant for reasons that I'll show you in a little bit more detail in this video. So if you can hold your horses for 15 minutes, we'll get there. What if the replacement green product has a much shorter lifetime, or expected anticipated lifetime, than the red product that we have here? So in this case, we've got a good quality product here on the red, and it might last for a long time, so years many, even though it uses quite a lot of energy in use. Now, if we were to say put a green product up there like this, we might find that the green product has a short lifespan, and in that case you're going to need to replace that green product whilst the red product would still be in service. So assuming that there's no recycling going on, every time that you replace that green product, you're going to increase your emissions. And in that case, it's basically never going to be worth replacing the red product, at least not until it's totally life expired. Now, I wish I could tell you that this is an unusual and rare occurrence, but unfortunately it happens quite a lot. So if the predicted lifespan of the more efficient product is short, then often it will not make any sense to replace it. A very big or sort of common example is fast fashion clothing in comparison to sort of high quality, I'd say locally manufactured alternatives. That locally manufactured doesn't mean in some twee village in the Cotswold. It could mean in India or wherever you live, but generally speaking, it's the high quality and the locally manufactured together that's the key here. Now, particularly since getting married, it's really rammed home to me the appalling quality of fast fashion, and especially in ladies' clothes. It's one of my wife's biggest complaints about it, is the quality of materials, of manufacturing, threading, labeling and so forth of ladies' clothes from the fast fashion industry is appalling. Even if you want to keep these things, they're falling apart or losing their color or losing their shape after one or two wash. I've put a picture of the Queen here, the former Queen, God bless her, sadly passed away now, and she was quite well known for wearing the same outfit many times over many decades, whereas obviously your H&M, your Zara, you know, your cheapos often get used once and then returned to the store. Now that is one of the worst things that you can do. I appreciate, obviously, that not many of us, including myself, can afford quality clothing like the Queen wears. However, we can often do a lot better than buying the very nastiest stuff off the shelf. I buy most of my clothes from Marks and Spencer's, which might fall into the fast fashion category for some people, but equally I've worn shirts and trousers from Marks and Spencer's that I've had for 10 plus years. Now, for a lot of people, that's not going to be an option, but let's ignore that massive elephant in the room and focus purely on emissions. Fast fashion is bad. Locally manufactured high quality fashion is good. Now, what if one product has a shorter lifespan than another product, but its emissions can be progressively reduced? So for example, if we build a product, in this case we've got the green product here, and it's got a fixed lifespan which is substantially shorter than the red product, and it has some embedded emissions here from manufacturing. But we maybe invest in new technology, like there's a new engineering development or there's some recycling or something like that. So the next time we build that product, it requires substantially less emissions from the manufacturing process. Now what that means is at some point it will break even with the red product, and it could be that the next iteration will be even more improved and it will outlast the red product at some point. So in this case, whether or not you buy that product will have to depend a lot on what information you have, and it's going to be very difficult to find that information, and you have to believe that these future advancements will take place. Now, in some instances, like batteries, for example, particularly lithium ion, it is very certain that this will happen because more and more lithium-ion batteries are produced. Lithium is an inherently valuable commodity which costs a lot of money to mine, and there's a higher and higher demand for it. It is true that there isn't much of a recycling infrastructure in place for it right now, but that is because there hasn't been a demand for the lithium, and there hasn't been a demand for recycling lithium-ion batteries because most lithium-ion batteries that have been built are basically still in use. Not on an individual basis, but certainly on a kilowatt hour basis. So at some point, it is completely reasonable to assume that lithium ion batteries will be recycled, and that will massively cut down the emissions caused by making them. I could have put, for example, early renewable energy technology such as early wind turbines. So wind turbines from the early days were very small, they didn't generate much power, and wind turbines today are big and produce much more power, and therefore the emissions versus the life usage generation is much better on a wind turbine now than it was 50 years ago. I put paper as just an interesting aside because, of course, paper doesn't really have any emissions during use. With paper, the vast majority, if not all of the emissions, come from manufacturing the paper. Then we might have a long life, for example, when the paper doesn't actually emit anything because it's just sitting there on the shelf. I mean, it depends if you want to include heating, ventilation and air conditioning and things like that as the lifetime generated usage emissions of the paper, but generally we wouldn't. Now, recycled paper always has a substantially lower amount of embedded emissions than virgin paper, and the only real disadvantage of recycled paper is that it doesn't last as long, but for many applications that just isn't relevant. Most paper, I would suggest, is used for cheap pulp newspaper, flyers, printing a few notes around the office that get thrown in the bin later. So for that kind of use, you don't need long life, high quality paper. And I'd posit that the only real reason to use very high quality paper of the type that can only be achieved in modern technology with virgin wood pulp is for very important long life applications such as archiving, artwork, or currency, paper money. A more common example that a lot of us might have is you already have something, you already have a product. Maybe it's a bit old, maybe it's a bit tired, and you're thinking of replacing it. Or maybe it's a product that doesn't really meet modern environmental standards and you're thinking of replacing it. Well, okay, let's say you own the red product and it had some emissions represented here, and then you're using it and it's creating emissions. And there's a new product, the green product, which has some emissions from manufacturing and a lot less emissions from use. If we plot them on the same chart at the point T, that's not a lot of good to us. However, what we can do is move that green line up there, and as we move along this chart with T going this way, we will find out that if we replace our red product with the green product at this T0 point, then at some point, Tx, we will reach a break-even point. And from that point, then the green product, assuming it's still alive, will represent a saving in emissions over the red product. That is so far so basic. Now the big question is, of course, will the green product last that long? So that really is requiring a sort of sense of clairvoyance and market analysis, and assuming that the green product will last that long, then you should, all other factors be equal, replace the red product with the green product as soon as possible. If you don't, if you delay replacing the red product with the green product, then all that you will achieve is raising the lifetime emissions of product use, because you will find that if you put a new time here, time 2, and you put the green product here instead, your break-even point has gone further out into the distance and your total lifetime emissions have gone up. So if you can, replace the product as soon as possible, assuming that you've got confidence that it's going to last long enough to reach break-even. If you don't, you're going to raise the total emissions. So good examples of this are almost all electric transport in comparison with internal combustion engine transport of the same kind. An older example, maybe one from sort of 20 odd years ago, is LCDs instead of old-fashioned cathode ray tubes or plasma units. Also, LCDs may also live longer than the lower quality cathode ray tubes. Not so much the Sony Trinitrons and things like that that are still kicking around in CNC machines and various industrial equipment, but the sort of cheapo cathode ray tubes that I might have had in my household definitely didn't last that long, and I'm already rocking LCDs that have outperformed them. LCDs obviously cost less to manufacture and they cost less to run in terms of emissions, so it's always a good idea to replace them. Now, I've already covered the fact that if you've got an available green product, it's good to replace the red product as soon as possible, but there is an exception to that. And the exception could be that if you genuinely believe that there's going to be a substantial improvement in the green product in the next few years, and you also believe that you can keep the red product running long enough to take advantage of it. For example, here I have a purple product, and the purple product comes into position a few years down the line, and it has a lower emissions related to manufacturing and maybe even a lower emissions related to use. Now, that may well be valid, but it's difficult to find examples of this kind of technology where the improvement is substantial enough that it's going to give you a really good reduction in emissions. So, for example, in this case, the total reduction in emissions as shown is relatively small, because even though the purple product is very much improved over the green product, the fact that it's taken that delay, and during that delay time we've been using the poor performing red product, means that the benefit of delaying isn't really there. And of course, you've got to be pretty confident that this is going to happen. So again, if we go back to electric vehicles, we can be absolutely sure that this is going to happen with electric vehicles, but in most cases it still doesn't justify making that big delay period, because electric vehicles are already pretty good and your internal combustion vehicle is pretty bad. I touched on this before with fast fashion, where I said, what if a potential replacement product can never break even? Now, that might not just be the case with fast fashion, where you have a very high embedded emissions from manufacturing and a very short lifetime. It may occasionally happen even if you have an improvement in the manufacturing emissions and an improvement in the use emissions, but a short lifetime. And in that case, it's never really going to make sense to replace your red product, as long as you can keep your red product going. And even more curiously, if your red product is lasting this long, then it would not even make sense to replace your red product at the end of life with a green product. It would make sense to replace it with another red product, because the total lifetime emissions of the red product are going to be lower than the total lifetime emissions of the 5 or 6 green products that you need to buy to do the same job. Depressingly, there are very, very many examples of this in our world today, and unfortunately, at a personal level, many of us come into contact with them a lot. So I would say almost all domestic appliances fall into this category. So modern domestic appliances are just not built very well. I've shown on the right here a personal bugbear of mine that I have no fear at all in naming and shaming, which is a Dyson. Now, Dysons are crap, and there's basically no nice way to put that. Now, people might wax lyrical about the centrifugal vacuum system and all this kind of nonsense, but be that as it may, the fundamental point is that not only are Dysons quite expensive to buy, but they're made out of the sort of plastic that I would normally associate with a chocolate box, and you just can't get the life out of them. I've inherited a couple during my time, and they've all died very quickly, whereas the Henry that I bought maybe 17 years ago now is still running. Now, I've talked about Henry Hoovers before. I think they're one of the most wonderful examples of a consumer product that's available today, because they are relatively cheap and they last forever, and the country that makes them, Pneumatic, has been making the same model for 1980 and still holds all the spares. So really, as an environmentally friendly product, I think you would struggle to do much better than the Henry Hoover, unless you go back even further to sort of the 1950s or 1960s, when you might have had equipment from the likes of Philips or Toshiba that would probably do even better. But if you happen to find that in a car boot sale, my recommendation is to buy it. Now, one of the reasons for this is that they were just made heavier. So a lot of people today don't like heavy appliances, but unfortunately, to quote Boris the Blade from Snatch,
heavy is good, heavy is reliable.
It's not just domestic appliances, however. You look at personal electronics, so if you think of an old Nokia phone and how indestructible it was compared to a modern smartphone, all of these things are built to lower quality standards than what they are typically replacing. Now, there's many reasons for that. Often it's just what the consumer wants. You know, they've been led into this lifestyle where there's constant developments in products and they constantly want new products. So why would they want a high quality product that would last forever anyway? It's completely understandable how this has happened, but that does not excuse the fact that it's happened, and it is a depressingly large problem. Occasionally in life we get a situation where you have an existing product which is both polluting and short-lived. So in this case I've shown you a red product which has got a very high emissions associated with manufacturing it and a high emissions associated with using it. And if we come down here to point T, which is where we are at the moment, we can see that if we then replace that red product with a new technology green product, that not only will the green product use less energy during use because the slope is much lower, but it will also last for a lot longer. So even though it uses more energy to make it, it will last a lot longer. If you find yourself in this situation, then there's really no excuse for not replacing that red product as soon as possible. Now, this situation does happen surprisingly often, but one of the most common examples, I'm sure you've guessed it, is as follows. And if you guessed incandescent light bulbs in comparison to LEDs, then you are correct, because of course incandescent light bulbs are terrible. Now, in incandescent light bulbs we get a very, very high startup where we make the thing, and then they use an awful lot of energy because they're so inefficient. So they only produce sort of 5% light, and the rest is heat. And they're not even a great heater, because as a heater, although they heat well, they don't last very long. So you'd have to keep manufacturing them. So even if you said, well, okay, I want to use these things to heat my house, there are better ways of doing that. Go buy an oil heater or a fan heater or something from the local B&Q, and it will last for much longer. Whereas an LED is at least 10, probably more times efficient, and it will also last at least 10 times longer. To be honest, I don't know how long they last because I've never had one fail on me, but certainly years many. And that means that LEDs get the Ollie Epsom seal of approval. So there we go. But many people still have incandescent bulbs kicking around, and in many places you can still buy them. For example, in Taiwan, my flat was full of the things, and this is doubly irritating in a hot country like Taiwan, because not only are you wasting vast quantities of electricity generating heat, but you're in a country where that heat is totally superfluous to requirements and then has to be removed by the air conditioning system at the cost of even more power and emissions. There are other similar examples to incandescent light bulbs do exist. This is one that I see a lot, and for those of you who say, oh, I don't like the light of an LED, I prefer the warmth of an incandescent bulb or whatever, well, for you, I really have no sympathy, and you need to put your prejudices aside and get with the bloody program. Let's look at a worked example, and the worked example we're going to start with is buying a new car. Let us assume that you are absolutely flush with cash and that either your existing motor has died a sorry death by the side of the road, or for whatever reason you're in a position that you want to buy a motor and you want it to be new. Now, I really can't overemphasize the fact that this is a bad thing to do. The best thing you can do from a point of view of reducing your emissions in this instance is to not buy a new car, right? So don't buy a new car, don't buy any car, don't have a car, get on your bike. So that is the best thing you can do. However, many people want a car, many people are going to go out and buy cars, and we don't yet live in a world where that's not going to happen. And it would also be very hypocritical of me to tell you not to buy a car, because I have one myself, and I suspect a lot of my viewers also do. But that doesn't absolve me of the fact that I know that it's wrong. So let's get into it. With a little bit, he said, of research, which means a lot of digging, I have come up with the following figures where I've compared a small car with an internal combustion engine, in this case something like a Nissan Micra, with a small car with an electric motor from the same manufacturer, which is the Nissan Leaf. Now, I have no affiliation with Nissan. I don't own a Nissan. I have never owned a Nissan. I've rarely driven a Nissan. I've picked these two cars because I live in the UK. Both of them are made in the UK, and I can have some degree of confidence in the figures that are presented based purely on that. Now, if we look at the manufacturing emissions of the petrol car, it's approximately 10 tons. Now, I'm going to go into that in a little bit as to why we have to treat these numbers with a high degree of suspicion, and why the biggest problem that you and I are going to have when we're making these decisions based on these models is getting accurate information in the first place. We are assuming on the same source that will be linked in the description if I remember to put it down there, and is linked below here for information, but of course you can't click that if you're watching this on YouTube, that the Nissan Leaf takes about 50% more, so about 15 tons of CO2 equivalent, because it has a battery in it, and manufacturing batteries at the moment is an inherently energy and therefore often emissions heavy business. Okay, but as we would expect, when we look at the emissions during use, the CO2 equivalent per kilometre, we find that for the small internal combustion engine car, it's approximately 0.15 kilograms per kilometre, so not too bad, but it's substantially less, 0.025 per kilometre for the Nissan Leaf electric car. Now, I know what you're saying. You're saying, but electricity. Okay, well, the electricity has to be made, and that's where these emissions come from. Obviously, the car is electric, but the power has to come from somewhere, and this is based on the UK grid mix. Okay, so the UK does have a substantial amount of renewable energy. Some days it's up to 50% now, and therefore the emissions from creating the electricity are much lower than the emissions from using petrol or diesel in your internal combustion engine. Even if, and I'll say you this in a little bit, but even if you live in somewhere like Poland or Taiwan, as I currently work, where it's mostly from coal, these figures will still be much better than burning the fuel directly in your car. And the reason for that is that a large thermal station is a much more efficient way of turning fossil fuel into energy than the small power station that you have in your car. So even if all of your energy comes from coal, you're still going to produce way less emissions driving an electric car, than an internal combustion engine car. It's just that you will create more than in this UK example. Equally, if we lived in Norway instead of the UK, this figure would pretty much be zero, because Norway is pretty much fully renewable in the electricity department, and therefore you could drive this car and create effectively zero emissions. I know that this does not include costs such as repair, rebuilding the car and so on, but we're just going to skirt around that issue for now. I have assumed that we're doing 15,000 kilometers a year because it makes the maths work. It doesn't really matter, but what is important in this case is that I've chosen the same amount for both vehicles. Now, what might happen in reality is if you buy one vehicle as opposed to another, you might like it more than the other, you might enjoy driving it more, and therefore you might do more kilometers in one vehicle than another. If that's the case, you're going to have to assess that at the beginning and put the numbers in. When we do the maths, which I'll show you graphically in the next slide, we see that the break-even point comes after only 40,000 kilometers, which in this case would be achieved in 2.7 years. Now that's a very, very rapid break-even point at a very, very low mileage, and we can have absolute confidence that even a really rubbish electric car is going to last 40,000 kilometers or 3 years. You know, that should be something that even a cheap Chinese import can achieve. Although we must be careful, because a cheap Chinese import is very likely to have a much higher embedded CO2e quota. Now, the total CO2e released over a 12-year, 180,000 kilometer life is about 37 tons for the internal combustion vehicle and just under 20 tons for the electric vehicle. So even though the electric vehicle generates way lower emissions through its life, it still isn't emissions free, and that's why I say even buying an electric vehicle is still bad, right? It's still not a good thing to do. You're still better off not having a car if you can. But if the decision you've made is that you want one or need one for whatever reason, then you are much better buying an electric vehicle than you are buying an internal combustion engine vehicle. I'm not talking about financially, I'm not talking about uses, I'm talking purely on the lifetime emissions that that product is going to create. I've put a couple of caveats down here, and I'm going to add this at the end, but if you go on Nissan's website and look at this link here, they will tell you that the fleet-wide CO2e emissions are 500 kilograms per vehicle for manufacturing and a further 310 for transportation. Now, if you add those figures up, that's only around 5% of what I've shown you here, where 10 and 15 tons. So what am I doing there? Well, it's not so much what I'm doing, it's what Nissan are doing. I think Nissan have not included the total manufacturing emissions. They have only included the emissions from the manufacturing stages that take place in the factories that Nissan own. Now, Nissan, the last time I checked, is not a battery manufacturer, and it is not a steel manufacturer, and it does not produce aluminium or copper or plastics directly in-house. So it does stand to reason that if all Nissan are counting is a little bit of metal folding and a little bit of welding and running the heater at the plant in Sunderland, then sure, it's not going to have many emissions. But the total manufacturing emissions is what we're interested in, and most sources suggest that they are nearer 10 to 15 tons. And this is a very important point, that you must beware of manufacturers' claims. Often a manufacturer might mean well, often they don't. Often they will try and confuse and obfuscate. Now, there's a common saying that we should not assume malice where incompetence will do the job. It is, for example, difficult for Nissan to know what their entire supply chain is doing, and even if they did, they might think, well, you don't want to double account it. However, in this particular instance, and again, I'm not taking particular aim at Nissan. None of the other manufacturers are any better. In fact, they're probably worse. After all, I could get some figures out of Nissan, which I couldn't get from anyone else. It is, in this case, not something I'm going to give them the benefit of the doubt on. We do know from history that companies like Big Tobacco, Big Oil, and so on are the cartoon villains of the world we live in. You know, they have done terrible things. It is not unreasonable to assume that they still are. So the biggest problem that you and I are going to have when we're using this model is finding out what these figures are, and because of that, it allows people to make completely ridiculous claims that, you know, electric cars, for example, are no better than internal combustion engine cars, even though there's no doubt that they are. The reason people can get away with making those sorts of claims is because the amount of data out there and the variation in the data and the way that that data compares apples to oranges is almost designed to allow a false debate to occur. Okay, I showed you it in a table form. Here we have in a graph form using the same methodology as before, the break-even point at 40,000 kilometers or 2.7 years. And you can see that there's really quite a dramatic difference when you see it graphically between the through-life emissions of the two vehicles. And that's why the total lifetime emissions of the EV will be approximately 50% of those of the ICE. Now that's obviously at the moment. Future vehicles may well be lower, but as I said before, if you delay, then you're still using your internal combustion engine vehicle, so the total emissions improvement won't be that much better. Okay, so that's what happens if you're choosing between an electric and an internal combustion engine car off the forecourt. However, not many of us are in a position to make that choice. A more likely scenario is that you already have a vehicle and you're thinking of replacing it with a new one. Now, let's use my personal example as a worked example for this. So I own a very old car, or what is by the standards of many people a very old car. I own a 2006 Honda CR-V with a 2.2 litre CDTI engine in it, and I've had this car for many years and it is bomb-proof and I like it. However, it is an absolute emissions monster and I've been considering replacing it for a number of years. Now, the figures, as best I can estimate, I've actually assumed it's got a similar amount of embedded emissions in it as the small car that I would be replacing it with a Nissan Leaf. This probably isn't true. It's a bigger car than a Nissan Micra, so maybe it has 12 tons, but let's keep the math simple and use 10 tons. The CO2 equivalent per kilometre I get from the actual manual, and it's 0.177, so not great. And we're again using the same Nissan Leaf we used before with the UK energy mix of 0.025 kilograms per kilometre. I'm using the same kilometres per year, and I'm saying that the current 2006 CDTI diesel engine has only done 220,000 kilometers, which is actually very, very low considering its age. And of course, the new vehicle will be new, so it won't have done anything. The total CO2 created by my current vehicle over its life, so 10,000 from being manufactured and the rest from being used, is about 55 tons. Obviously, the new car will have 15 because it's just been built. Now, if we do the maths, again, I'll show you the graphical in the next slide, we get the break-even point will be 98,550 kilometers or 6.57 years. So much further than if we're comparing new to new, because of course I've already got this car. I'm not creating more emissions by manufacturing it. I already have those manufactured emissions, so it takes longer to pay off, as we saw before. And at that break-even point, you will have created a total of 72 tons of CO2 over 23.57 years, of which the amount generated by the EV is almost nothing. It's just 17.5 tons as opposed to that created by the Honda, which is 55 tons. So we can see that, again, there is no excuse from an emissions point of view for me to not make this change. The only difference is that it takes longer to pay off. But again, we can be fairly certain that a good electrical vehicle from a reputable manufacturer like Nissan is going to last 6.57 years or 100,000 kilometers. We cannot be so certain for some of the cheaper imports that we might get from our cousins and friends in the People's Republic. Okay, I showed you it on the table. Here we are showing it graphically, the same as before. And I'd just like to reiterate the fact that we are here at time 0, and that's 17 years of operation of the existing vehicle. And just to make the graphics easier, I've used 34 years, which is 2 times 17 for the total length of time that we see here. And after our break-even point, which happens at around 100,000 kilometers at 6.7 years, we can see that after that we start saving a lot of energy. So there really is no excuse for me not to do this based purely on the basis of emissions alone. Not only that, my car is 17 years old, it's getting tired, I need to make a lot of repairs to it, so those repairs will engender a lot of additional emissions. For example, new brakes, new suspension components, bushings, steel, all that kind of thing, all has embedded emissions in it. Interestingly, not only would an electric car use less energy and therefore create less emissions during use, but things like the brakes would not wear out as much because of regenerative braking. Now, as I said before, technology is improving all the time. So if I choose to keep my car on the road, I could, for example, suggest that in the foreseeable future, so I'm thinking 4 to 5 years, substantial improvement in battery technology will be there, and therefore we'll get a much lower embedded cost of the manufacturing of an EV. As we've already seen, the manufacturing emissions of an internal combustion engine are about 10 tons and the manufacturing emissions of an EV are about 15. So if we go 10,000 kg versus 1,500 kg, sorry, 1,500 kg, we could see that in the absolute best case scenario, of perfect batteries, we'd probably still be around the 10,000 mark, because if you take away the batteries from an EV, what have you got? You've got a lot of steel, a lot of plastic, a lot of electronics. You've basically got an ICE car. So this very substantial drop that I've shown here is unrealistic. A much more likely drop is it will be roughly 10 or maybe 9, in which case I am not going to reduce my lifetime emissions and I'm still better off replacing it now. As I mentioned, cars are a consumer product, for example, and a good quality car will last a long time. Obviously, if I buy a rubbish quality electric car, then I'll be back to square one, as I mentioned earlier, and my lifetime emissions will be low, assuming that I could keep the Honda on the road, which I'm absolutely certain I can. Now, because of that, a much better solution would be to scrap my car and go without. If I scrap my car, I would reduce the transport emissions to pretty much 0, because even the worst public transport system is so much better than private transport that it's really not worth worrying about. But if you're lucky enough to live in an area with really good quality electric public transport, then there is even less excuse. So, for example, where I currently live and work in Taipei, there's a very good transport system, and it baffles me beyond words why anyone has a car. But a lot of people do, and they don't just have small city cars, they have sodding great 3.5, 4.8 litre V8 petrol status symbols that they drive around the little streets as a way of demonstrating that their genitalia are more impressive than mine, which I think we all know is probably the case actually. Now, in general, for products with low operating emissions, which is a lot of household equipment, so cars are pretty much an exception in this case, that they have a very high emissions from use. Things like anything that burns fossil fuels does, like your household boiler and so on, but a lot of other products don't. A lot of other products, a lot of the emissions are from making the thing. The best solution is just to buy less stuff, use it less and keep it for longer. So really rebel against this disposable culture as much as we can. So we can all take some steps to do this, and I 100% recognize that there are very limiting factors for the vast majority of us to make substantial improvements here, but all of us can make some improvements, even if that's limited to, say, patching up our clothing with a sewing kit at home. Now, before I go into that in more detail, I'd just like to show you the following interesting chart, and it comes from this source here, which is a source that I've used in part to create the figures that I showed you earlier. Now, what this does is it's slightly different to what I showed you. It's showing the total life cycle greenhouse gas emissions, but instead of showing it to you versus time, it's showing it for the total life of the vehicle, and that total life will be based on some figure of kilometers. I think it was 200,000, but I can't remember exactly. So basically, if you say 200,000 kilometers of life and the manufacturing emissions and you add them all together, you get the total emissions, and then if you divide that by the distance traveled, you can get the emissions per kilometer throughout the total life. Now, what you can see here, interestingly, is that if you do the maths, the total emissions of conventional vehicles are worse than hybrids. They're worse than an electric vehicle with the European average electricity mix, and they're worse than any of these other electricity mixes. So, for example, Germany and the United States of America have pretty poor dirty grids, and even then, the total emissions per kilometer from manufacturing and use for an electric vehicle is substantially lower than it is for a conventional vehicle or even a hybrid. And that is what I was saying earlier, and I just thought I'd show it to you in graph form. There's another point I'd like to make here, which is for the conventional vehicles, the grey represents the tailpipe emissions. So that's the 0.177 kilograms per kilometre that, for example, my vehicle creates. What the orange section here is, I did not even include in my figures deliberately, just to not muddy the waters too much, but that is the fuel cycle emissions. So that fuel cycle emissions are, in the case of a conventional vehicle, the cost of refining the fuel, so mining and refining whatever fuel you're putting in there. I didn't even include that in the 0.177 kilograms per kilometre, so you can see that that adds another 20 or so percent. For the electric vehicles, that fuel cycle here represents the generation of electricity. And that is why there is a difference between the various countries, because in some countries like France or Norway, the generation of electricity is super clean, whereas others like Germany or America, it is not super clean. Now, the dark blue represents the manufacturing of the vehicle for conventional and hybrid, and the light blue represents the manufacturer of the propulsion battery. So a hybrid's got a fairly small propulsion battery, so you can see a small sliver of light blue here. Obviously electric cars have a big propulsion battery and normal vehicles don't at all. So that is why you can see that the manufacturing costs of the non-battery section of the EV are about the same, maybe a little bit lower than a conventional car. But of course, the manufacturing costs of the battery are high, and that represents, or that is the reason rather, why the total cost of manufacturing an electric car are higher in terms of emissions. If you drive your EV in Norway, you'll basically have zero user emissions, but of course, you'll still have all the embedded emissions from manufacturing the vehicle in the first place. What is interesting is that the manufacturing emissions for the batteries, that's that light blue point, will vary substantially for the same reasons. So in this chart, all the batteries are the same because it's compared the same vehicle. But if you buy a vehicle with batteries made in country A versus batteries made in country B, this amount will vary a lot. Batteries require a lot of energy in order to make them, and a lot of that energy is in the form of electricity. So if you make your battery in a country with a very dirty grid, then the emissions inherent in making that battery are going to be much, much larger than if, for example, you made them in Norway or France. Now, at the moment, an insignificant quantity of batteries are made in Norway or France. I'm not sure if they make any at all, to be honest. Most batteries are made either in China, which is by far the biggest, or maybe America. Now, although I've singled out Germany and America here for having dirty grids, which they do by sort of Western European standards. Those grids are pretty clean in comparison to China, which would be 2 or 3 times worse. So batteries from China are going to have a higher embedded CO2e equivalent figure than those from America. So again, when we look at these kind of products, we really need to think about where they're coming from and what technologies they're using, because there is a very big variation there. Throughout this talk, I've avoided the elephant in the room, and we all know what the elephant in the room is. The elephant in the room is money. And it's not really going to be possible to finish this presentation without talking about it. First off, I want to go over this concept of Vimes's Boots' theory. Now, it's not really a theory, it's a passage from a Terry Pratchett book, but nonetheless, I think it's relevant to what I'm about to talk about. So the reason that rich were rich, Vimes reasoned, was because they managed to spend less money. Take boots, for example. A man who could afford $50 had a pair of boots that would still be keeping his feet dry in 10 years' time, while a poor man who could only afford cheap boots would have spent $100 on boots in the same time and would still have wet feet. Now, obviously, in a great macroeconomic sense, Vimes's Boots theory can't really be rolled out, but nonetheless, in the sense that we're talking about, it can be. I've shown you a method for comparing two products based on the emissions, but 99% of us have to make those decisions based on money. If I take the incredibly self-centered and unnecessary example that I've already shown you of a car again, and if I put money on the vertical axis and time on the horizontal axis, I'll get the same kind of bent line. So I'll have to spend a lot of money to buy a new vehicle, and then because it's quite cheap to run, I won't spend that much during its time. Or I could keep my old one, which would require a lot of expensive repairs every year, and it costs more in diesel and so forth. But even then, if I do the maths, that break-even point isn't 2 years in the future, it's not 6 or 7 years in the future, it's 24 years in the future. So the reason that I haven't done that is because it doesn't make economic sense for me to do it, because it would take me 24 years to get my money back. Now, that does somewhat relate to Vimes's Boots, albeit in a very trivial way, in terms of the fact that during that time, I've obviously got a dirty, smelly, rusty car that's falling apart, and if I keep on with it, right, because I'll never have money to buy a new one, if I extend that line to 40, 50 years, you know, I will end up spending more than if I'd just bought a new one. Obviously, however, cars are a trivial thing in comparison to boots, but nonetheless, I think Vimes's concept is useful. So the situation is that although rich people, it's fair to say, do cause most pollution, so biggest polluters per capita are places like the United States of America, Europe, Australia and New Zealand, United Arab Emirates, all those sort of other sandy places. Per capita, these are emissions monsters, and not only that, until very recently, the United States was the biggest absolute polluter, whereas now China is. But China's population is 3 or 4 times that of the United States of America, so on a per capita version, China isn't as bad. Notwithstanding that, however, it is reasonable to point out that all of those countries, America, Europe, Australia, New Zealand, and so on, not the United Arab Emirates, but they're an outlying case, are making steps to improve their emissions. And this is going to happen naturally over the next few years as greener grids come in, more electric vehicles, less polluting farming methods, etc. These are all countries that can afford to do that, and to some extent are. But the problem is that poorer countries can't afford to do that. And I'm not really just talking about China, which allegedly is a middle income country now. I'm talking about countries further down the economic development list, like those in Africa or other Southeast Asian countries, can't afford to do this environmentally friendly stuff. Now, why is that? Well, the simple reason is that polluters don't pay. We as consumers do not pay the cost of the pollution that we cause, at least not directly. And that really is the fundamental choice. I can emit pretty much as much carbon dioxide as I feel like, and nobody is going to come up to me and say, Ollie, please foot the bill for this flooding in Bangladesh, or please foot the bill for this wildfire that's destroyed half of the Amazon. That's just not going to happen. I know what you're going to say. You're going to say, I have to pay vehicle tax, which I do, and I have to pay fuel duty, which I do, but the amount of money in them, substantial though it is when I'm paying for it, is a drop in the ocean compared to the damage that that pollution is causing. So as long as we live in a world where the earth gets stuffed with a bill, we're going to live in a world where it's cheaper to just pollute than it is to not pollute. And in that situation, it's only going to be the rich that can do it, and the poor are just going to have to crack on and pollute everything and live with the consequences. And of course, the poor are most likely to suffer from those consequences. Now, this is therefore a political and an economic and a societal problem. And I don't know what the solution is. I am obviously a very strong critic of late stage Western capitalism, but that does not mean that I think that a better system has ever been tried or achieved. I think a lot of better systems may have been conceived, but I think that when those systems have been executed, they have been unable to cope with the fundamental flaw in humanity, which is human greed. So you may, for example, read Karl Marx and go, okay, that sounds great, we should try that. And you may have a point, but Karl Marx didn't take account of human greed. And when sort of Marxist or Leninist or Stalinist societies have been tried, they are not the sort of places that I would want to live, and I doubt they're the sort of places that you want to live. Equally, we've tried things like theocracies, we've tried technocracies, we've tried various forms of dictatorship, we've played around with communal sort of places. None of these systems generally work. I would say that the free market capitalist system is the cause of, but also the solution to all of our historical problems. It's very easy to see how we've got to this point, but I don't know how we get out of it. And I don't think the solution has been made yet. However, it's pretty clear that we do need political push towards making the polluters pay and somehow transferring that money towards more environmentally friendly development, and that does need to happen on a worldwide scale if we are going to improve. Now, if we don't do that, things are just going to get so much worse. In summary, then, let's close out. We've looked at a very, very simplified system for deciding what products to buy and when based on their CO2e emissions. But I stress that it's highly simplified, and I've put many caveats throughout here. Deploying this system in the real world can be very complicated due to the complex data and the need for reliable estimates on future conditions. This really is the crux of this. To find out the data is hard. Often it doesn't exist. Often it has to be estimated from macro figures that might apply to an industry in general, even though that industry could have wildly different emissions depending on where it's made and what technology they use to make it and so forth. So real world, this is difficult to do. Most of us are not able to invest purely based on environmental reasons anyway, and the poorer we are, the worse we're going to be affected. So although I've developed or demonstrated this simplified model, most of us are not in position to do what it says other than go without. But even going without will come at a cost. By far the best option for most of us is to buy less, buy the highest quality available and use it less and keep it longer. But we have to appreciate that in many cases that's just not an option for people. As long as it's the earth and not the consumer paying the bill, the situation is unlikely to change until individuals feel that the earth demanding debt repayment. So what I mean by that is, at the moment, although global warming is absolutely happening, although climate disaster is happening, although wildfires are happening, water problems, the vast majority of people, individuals, still don't feel that climate change is affecting them or will affect them in the future. So we are quite happy to keep the earth paying the bill, and it's not going to be until enough of us feel that debt repayment demand from the earth that things are going to change, even though we really need to change them now. So thank you very much for paying attention during this talk. Obviously, if you've got any comments or observations, feel free to throw them in the comments box where I will pay them the attention that they deserve. I will catch you later, and thanks again. Take care now.